Some objects in space don't just emit light, they behave like unstable transmitters. Magnetars are neutron stars that can snap under magnetic stress and fire bursts that hit satellites, radio telescopes, and X-ray instruments almost at once. Their signals repeat, spike, vanish, then return, like a machine with a broken switch. Tonight we follow the evidence, starquakes, giant flares, and the magnetar events that reshaped the FRB debate. A magnetar is a neutron star, the collapsed core of a massive star after a supernova. It's incredibly small and dense, with gravity and pressure far beyond ordinary physics. But the defining feature is the magnetic field, so extreme it dominates the star's behavior. For magnetars, magnetism is the fuel, the trigger, and the amplifier. The magnetic field can trap and accelerate charged particles, shaping bursts and beams in the magnetosphere. It can twist like a loaded spring, storing energy for years and releasing it in seconds. That's why magnetars don't need external fuel to flare. The field itself is the reservoir. When the twist changes suddenly, the sky lights up in high-energy flashes. Magnetars are born in the aftermath of massive star death, inside expanding supernova debris. In some scenarios, a rapidly spinning newborn neutron star can amplify its magnetic field to extraordinary levels early on. The surrounding remnant becomes the crime scene tape, filaments, shocked gas, and a compact source at the center. Many magnetars are linked to these remnants, tying the signal machine to a violent origin. A magnetar has a rigid crust over an ultra-dense interior, and the magnetic field can torque that crust over time. Stress builds until the crust shifts or fractures, like tectonic plates, but on a star. This sudden motion is a starquake. The quake can pump energy into the magnetosphere and trigger rapid high-energy bursts. Some magnetars were first recognized because they produced repeated gamma, X-ray bursts, short, clustered flashes instead of a single explosion. That repetition is the key. The system can recharge because the magnetic field continues to evolve. Bursts can come in storms, dozens within hours, then silence. It looks coded, but it's a stressed object unloading energy in bursts. A giant flare is the magnetar's extreme limit, an outburst so intense it can saturate detectors and trigger instruments across space. These events can have a sharp initial spike and a longer tail modulated by the star's rotation. They're rare, but they prove magnetars can output staggering power in moments. If you want the most violent signal, giant flares are the exhibit. When a giant flare hits, multiple satellites can register it nearly simultaneously, each with different sensitivities. That multi-instrument signature is why magnetar flares are not folklore, they are recorded events with cross-checks. The same event can show prompt gamma rays and follow-up emission as the system cools and reconfigures. The signal looks like an alarm trip across the entire high-energy monitoring network. Magnetars often rotate in seconds, imprinting a periodic rhythm on what we observe. Even during outbursts, you can see the rotation modulate the tail like a lighthouse. That combination, random bursts plus a steady clock, is why magnetars feel machine-like. Nature built a transmitter out of spin and stress. Magnetars can spend long periods quiet, then suddenly enter active phases. Small changes in magnetic twist can alter pulse shapes and brightness dramatically. This makes them unpredictable and hard to model, but perfect for mysteries. The on-off behavior is not evidence of intention, it's evidence of unstable internal conditions. Fast radio bursts are millisecond radio flashes, sometimes repeating, sometimes one-off. Magnetars fit the requirements: compact, energetic, able to burst suddenly and repeatedly. The magnetar hypothesis gained major traction when a galactic magnetar produced an FRB-like radio burst detected by radio instruments. That doesn't mean all FRBs are magnetars, but it means at least some can be. Models include magnetic reconnection, crust-triggered magnetospheric shocks, or relativistic outflows colliding with surrounding plasma. The hard part is producing coherent radio emission, radio waves that act in step rather than as random noise. Magnetars may provide the extreme conditions needed for coherence, but FRBs are diverse, suggesting multiple channels or environments. Repeating bursts feel like a beacon, and humans immediately assign purpose to repetition. But magnetars naturally repeat because stress rebuilds and releases in cycles. Some repeaters show patterns, others are irregular. The challenge is separating physics cycles from our pattern hunger. Above the surface, magnetar magnetospheres can be twisted and unstable, with reconnection events that rapidly rearrange field geometry. That region shapes what we see: pulse profiles, burst spectra, and afterglows. A small shift in geometry can change the observed behavior drastically. The magnetosphere is where internal stress becomes a signal. Strong flares can energize nearby plasma and produce afterglow-like emission across wavelengths. In dense environments, interaction can leave detectable signatures in the surrounding nebula. This is the footprint of a signal machine, a small star altering a much larger region. It's one more way to test the story beyond a single flash. Pulsars are rotating neutron stars whose emission is powered mainly by rotation and magnetospheric processes. Magnetars are neutron stars where the magnetic field's stored energy dominates, leading to starquakes and burst storms. Both can pulse, but magnetars are the chaotic extreme. This difference matters because it predicts what signals to expect and when. We still don't fully understand why only some magnetars become strong radio emitters. We don't know how often giant flares occur across cosmic history or what fraction of FRBs they can explain. And we still lack one mechanism that reproduces every burst shape and repetition pattern. Magnetars are real, and still partially unread in their details. Magnetars are the universe's most violent signal engines, measurable, repeatable, and sometimes terrifyingly bright. Their machine behavior is physics, magnetic stress, crust failure, reconnection, and rotation. They may explain a portion of FRBs, and they definitely teach us how extreme matter behaves. Comment: do you think magnetars power most FRBs, or only a special class? And subscribe to World of Mysteries.